Have you ever thought high frequency trading firms trade within microseconds or even nanoseconds faster than you can even blink your eyes? Let's go deep and understand the complete HFT system architecture and technology behind this ultra low latency trading system. Everything starts at the exchange. The exchange continuously broadcasts real-time market data stream containing order book updates, trade execution, bid and risk changes, market depth information, and market events. Now, these feeds are transmitted at extremely high speed using multicast UDP protocols. Professional trading firms generally avoid standard broker API because broker API introduce additional latency. Instead, institutional systems consume direct exchange feed such as Nasdaq ITCH, OUCH, fixed binary market protocols. Now these feeds are delivered directly into co-location server located physically near the exchange infrastructure. Now you can ask a question, why is co-location so important? Because latency is fundamentally a physics problem. Even the physical distance between the exchange and your server matters. Every additional meter of fiber cable introduces propagation delay. In high frequency trading, microsecond matters. So firms place their server inside exchange data center to minimize transmission latency. Once market data packets enter the server network interface card, the next challenge is processing those packets as fast as possible. Traditional operating systems networking stacks are too slow for institutional HFT systems. Normal Linux networking introduces kernel interrupts, context switching, buffer cupping, scheduler delay, and unpredictable latency spike. To avoid all these, HFT systems use kernel bypass networking technology such as Solarflare, Open Onload, DPDK, RDMA, BG pooling, and hardware timestamping. Instead of packet traveling through the operating system kernel, packets are mapped directly into user space memory. Now this removes unnecessary overhead and dramatically reduces latency. But low latency alone is not enough. Institutional systems focus heavily on deterministic latency. Now deterministic latency means every packet is proceed within predictable time boundaries. Now predictability is often more important than the raw speed itself, especially for market making and latency arbitrage system. After packet capture, the data enter the market data engine. This is one of the most critical component of the entire architecture. Now the market data engine is responsible for feed fudging, message decoding, packet sequencing, gap recovery, tick normalization, timestamp synchronization, and full order book reconstruction. Now institutional systems maintain complete in-memory order book for every instrument being traded. Means in this order book it contains every new order, every cancel request, every modification, every trade execution, and every market event update in the memory book in real time. These systems are usually written in highly optimized C++ or Rust language. Now, memory allocation is carefully controlled. Cache optimization becomes extremely important here. Lock-free architecture are commonly used to avoid synchronization overhead. Now, garbage collected language are usually avoided inside latency critical execution path because garbage collection pause can create unpredictable latency spike. Once normalized market data is generated, the information must be distributed internally across multiple components of the trading system. This is handled by the real-time event bus. The event bus distributes market events to strategy engine, a risk system, monitoring service, analytics pipeline, and execution systems. Ultra-low latency communication technologies are used here, including shared memory queue, Aaron, nano message, log-free, ring buffer, and low latency Kafka pipelines. One of the most important concepts here is zero copying messaging. Why? Because copying memory repeatedly introduces additional latency and CPU overhead. Institutional systems try to minimize memory allocation, serialization, deserialization, and unnecessary data movement. Efficient internal messaging architecture is critical when processing millions of market events per second. Next comes the strategy engine. This is where trading decisions are generated. Different firms deploy different category of trading strategies. These may include market making, statistical arbitrage, cross-exchange arbitrage, latency arbitrage, ETF arbitrage, option volatility strategy, or machine learning prediction models. Now, the strategy engine continuously consumes real-time order book data and market signals. Now, based on the mathematical models and market microstructure analysis, the strategy decides whether to place order or modify quotes or cancel position or hedge exposure or react to liquidity imbalance. Before any order reaching the exchange, it passes through the risk and order engine. This component is responsible for real-time pre-trade risk validation. The system checks maximum order quantity, position limit, portfolio exposure, fat finger protection, symbol restriction, price validation, strategy risk limit, and kill switch control. This is one of the most difficult engineering problem in HFT architecture because the system must providing strong risk protection without adding measurable latency. The risk engine must therefore be both extremely fast and extremely reliable. Once an order passes validation, it moves into the order gateway. The order gateway handles smart order routing, exchange connectivity, protocol translation, and low latency transmission. Orders may be transmitted using fixed protocol, native binary exchange API, or proprietary exchange gateways. Smart order routing system may decide which exchange, which liquidity venue, which dark pool, or which gateway provides the best execution opportunities. Once the order arrived at the exchange, they enter the exchange matching engine. The matching engine processes price priority, time priority, queue positioning, trade matching, and partial fills. Execution reports are transmitted back through order gateway and market data feeds. Institutional firms continuously analyze fill quality, queue position, execution latency, slippage, adverse selection, and market impact because execution efficiency directly affects trading profitability. All market events are continuously stored inside historical tick database. This creates the foundation of research, backtesting, simulation, analytics, and machine learning. Institutional backtesting is very different from retail backtesting. Professional systems replay full depth order book, nanosecond timestamp, market microstructure behavior, queue dynamic, and exchange latency condition. This enables highly realistic simulation environments before deploying strategy into live market. Another critical component is system monitoring and observability. Production HFT infrastructure continuously monitor network latency, packet loss, queue depth, CPU utilization, memory usage, exchange connectivity, throughput, rejected order, and execution health. Because even small infrastructure problem can destroy strategy performance. Now, institutional trading firms therefore build advanced latency dashboard, anomaly detection system, alerting framework, and operational analytics pipelines. Now, monitoring is not optional in production HFT system. It is absolutely essential. Modern high-frequency trading is no longer just about algorithm. The real competitive edge comes from infrastructure engineering, low latency networking, deterministic system, hardware acceleration, real-time risk control, market microstructure optimization. That is what separates institutional grade trading systems from retail trading platforms. At Quant Alpha, we design and build institutional grade trading infrastructure for hedge funds, proprietary trading firms, and professional traders across global market. If you want more deep technical content on HFT system, FPGA trading infrastructure, exchange connectivity, market microstructure, low latency architecture, or institutional trading technology, subscribe to this channel.